Welcome everybody to this workshop on federated machine learning in life science. I'm Ola Spjut. I'm the AI coordinator for SciLifeLab Data Center, and together with Andreas Hellander, I will be giving this first presentation. So this workshop is first 45-minute presentation, introduction to the field, where I will give a bit of an introduction, and then Andreas will talk more about federated machine learning as a methodology. There will be, after the 45 minutes presentation, there will be a short break, time for questions, and then at 2, those of you who signed up for the hands-on workshop, we will join another Zoom link that has been sent out by email, and we will then do some hands-on hacking and try to set up a joint federation and get some hands-on experience using FedML, which is the system that we will use for this workshop. So I will first say a few words about me and Andreas. So we both work at Uppsala University. I am professor at the Department of Pharmaceutical Biosciences, and Andreas is at the Department of Information Technology. Andreas is also the director for Essence, the e-science strategic research area. As I said, also I represent here SciLifeLab Data Center. We should also point out that both me and Andreas are co-founders of the startup company Scaleout that is very much involved in federated machine learning. So the sort of starting point for this presentation is the data-driven life science program, the research program that I think everybody should be aware of nowadays. It's been a lot in the news. Large investments from Knut Alice Wallenberg Foundation channeled through and hosted at SciLifeLab in 4 research areas, and with a number of strategic recruitments ongoing. You should have seen a lot of ads come out regarding this. So there will be some very interesting recruitments starting up soon in the different connected universities to the DDLS program. And very central to the DDLS program is, of course, data. It's not just in life science, of course. If you look at the most highly valued companies, well, data is a very central asset for many of them. And in the data-driven life science, this will, of course, be put on a high effort will be directed towards both managing data and working with data. And it's already now today at SciLifeLab prioritized. Data sharing is a very central component at SciLifeLab right now, and it will be so even more in the DDLS research program. This is just one example of from SciLifeLab Data Center, the COVID-19 data portal that was specifically set up for this towards this aim, and really try to accelerate research through data sharing. And this has been very successful, both on a national but also on a national, international level. But I'd like to sort of raise this point: do we always need access to data? Well, obviously not always, and we can just very easily get answers to questions without actually accessing data. One of the simplest way that we do in many cases is that for example, we go to some website and we use a web portal that sits on top of data, and we can use that to answer a lot of scientific questions. Another way of doing sort of not using data but still getting responses to answers to questions is to use, for example, a pre-trained existing AI model, and that we just use, and we don't have to train it. So there is some ongoing development at the SciLifeLab towards this end, and really towards working towards fair, findable, and interoperable AI models that sort of to propel this work towards fulfilling all of FAIR, findable, accessible, interoperable, and reproducible. And also to target the AI model lifecycle. It can be rather complex to develop models, and right now it can be even more demanding to sort of serve them. So we want to make some efforts towards production grade serving of models and apps connected. This is in development. You will hear more about this soon. But in many cases, we need access to data. For example, if we have new types of questions where we don't have pre-trained models, or we want to combine data from different sources, then we really need it to answer questions. And a key problem is that a lot of the data is isolated, and there could be various reasons for this. For example, that people do not want to share. It could be private or proprietary data. It could be regulated, that we are not allowed to share data, and this is often the case in medical science. But there's also could be practical blockers that you cannot share because, for example, the data sets are large and it's practically difficult to move data around. But in many cases, we really want to have collaborations, and we want to have data collaborations. For example, we might want to collaborate to create something better that could not have been done in isolation, or solve a common problem, even if that means collaborating with, for example, a competitor. And privacy preserving data analysis is really trying to answer the question, how can we enable personal data to be shared without compromising our privacy? And there are a number of questions relating to this, and this is a research topic that a lot of people are working on. For example, how can we find secure ways of providing public access to private data sets? How can we enable joint analysis on private data held by several organizations, outsourcing of private data for computations on private data, or sort of securely decentralized services that rely on private data from individuals? So there are organizations and research groups working a lot towards these types of problems. Data Shield is probably one of the most well-known in the life science community, and it has a clear focus on epidemiology. And what they have done is that they've set up a system that relies on R, so that you here, as a researcher on the bottom line, you do analysis in R Studio Server, and then you can analyze the data that you have and also co-analyze data in other locations. But there are some computational and statistical controls implemented so that you prevent information disclosure. So you will not see individual data points from other partners, but you're able to still do statistical analysis based on the collected data. So this is a project that's been going on for many years, and it's implemented in many cases. For example, here, I think it is at the Uppsala Clinical Research UCR. It has had a clear focus on epidemiology, but there's a lot of development here that are interesting for other fields as well. Here is another project that my humble contribution to this field about combining predictions. I worked with pharmaceutical companies, and they would not agree to share their data in drug discovery projects. So we were working on how trying to then say, okay, but can we aggregate results from predictions, so that we would send the query on the right-hand side here to the different models, each trained locally, and we would then aggregate the predicted results. In this case, it was prediction intervals, and see that if we combine these predictions, can we sort of improve that, so that they would not share data, but they could share results from a prediction. Well, the challenge is, of course, in this case, that maybe the question sent out can be sensitive, so it does not solve that problem, and especially in drug discovery, that if you're working on new leads, that could be very sensitive. But this was this works well, of course, in some cases, and can be an alternative. But today we're going to focus on federated machine learning, and in this case we have multiple data residing at multiple sites, and we would like to train a joint AI model over them without the different sites, the different partners disclosing data with each other. So what this could be, for example, that data is sensitive from say human subjects or patients. It could be because data are big in many cases when we generate large-scale imaging and so on. It's moving the whole data sets is just almost practically infeasible. Or as I said, that data valuable, and exemplify this with the sort of drug discovery projects and pharmaceutical companies. But they all have some shared problems. They all want to, for example, predict some sort of toxicity endpoint, different toxicity endpoints. And it's a bit, they all see the advantage if all companies could jointly train a pre-competitive model for various types of toxicity. So this is something that we're working on together with some partners to try to get this implemented. So there have been some recent publications that have received some attention. I like this report that came out last year, Federated Learning in Medicine, where they showed that federated learning among 10 institutions resulted in models. They reached 99% of model quality when they compare to centralizing all this data. And they do a simple federated learning that they have a model that they then send around and do incremental updates across the departments until you reach a final model. No data is transferred, only incremental updates in a way that it preserves privacy. And Andreas will talk more about this later. This was for working on MRI images for distinguishing healthy brain tissues from tissues affected by cancer cells. And the most recent development in this is from the company HPE, and they term their federated learning approach swarm learning, and they combine federated learning with blockchain networking, and then demonstrated that this in a large-scale study to predicting leukemia from blood transcriptomes, and they were also able to predict tuberculosis and lung pathologies from X-ray images. And they show that by using it's federated learning with blockchain, they outperformed models at the individual sites, so that there was a benefit of these different partners jointly forming a federation and training a global model together. Now, with this, I would like to conclude my introduction, and I will hand over to Andreas. So would you like to share your screen, Andreas?
I would like to do that, definitely. So let's see here. There we go. Yes, so I will take over here and I will talk a little bit about federated learning, which is a core focus in what we do in this company Scaleout that Ola mentioned, but also in particular in my research group. So in my lab, we are running a couple of different federated learning projects, both centered on applications and but primarily then on the methods development. And just please interrupt me if you have any questions or if I'm going too fast or too slow. It's okay to just ask away if you want. Just to reiterate, I mean, the problem we're trying to solve technically is what Ola mentioned, that you have a problem in many situations with centralizing data, and it's like the private and proprietary data that Ola covered quite well. In addition to this, we also have practical situations where you say we something called fog and edge computing, where we have data that is generated close to the edge, where it can also be completely impractical to centralize the data, even if there is not a privacy issue. And also in this situation, federated learning is interesting. But then, I mean, to take a step back and look at the promise of federated learning, and what we typically have, I mean, what research looks at a lot is that the idea would be that we would be able to create a federation and train a model that performs on par or better with the best model, or ideally better the best model that you could train on the theoretical pool data that you don't have. And this is important. I mean, you don't have the pool data, but if you did, we want federated learning to arrive at an accuracy level or a performance level according to what you define there, on par or with this pool data. So in theoretical sort of situations, it should be able to arrive at the same accuracy. But more importantly, we wanted to outperform the best model that we could attain in isolation. And that's like the more realistic situations. But in research, we look at both of these things. So a typical example here, you see to the figure to the right there, and this is the model that we're going to work with in the hands-on as well. It's a model of a recently published model from a paper where you predict blood cell cancer types and their stages. And then you can see what the curves I have here that we took the sort of entire data set, which is about 17,000 images, made sort of in this case 10 partitions of this data. So you have 10 different clients or members, if you wish. So the blue curve you see there is the best one the best of these 10 that you could train using only that client's data. And then the orange curve is the one that you obtain if you take all the data and train a standardized, centralized model. And the green one then is like if you do it with a federated training. So as you can see, this kind of, and it's something we typically see across research initiatives for at least for imaging use cases. So this is a quite typical outcome. What you can also see then is that the federated training can struggle, has potentially a slower convergence rate in terms of total rounds. So this is a consequence of the algorithm. But the picture that we have in mind is the one to the left here, where you have some sort of orchestrator that coordinates sending out requests to clients. They can do updates of the model. These updates are sent back, and somehow these things are aggregated together. And the most common algorithm, if you start reading about this, is called federated averaging. It's from a paper, I think it's quite recent, from 2016 or 17. It's really a version of local SGD. But in principle, and you don't have to read all of this, but in principle, what you do is that you, as I said, you fan out the training to all the clients. They do an update of the model. The model has some parameters. So in the case of neural networks, these are the weights in the network. So these are sent back to an aggregator, and then a weighted sum is computed. So that you essentially obtain the average, the weights in the centralized model by averaging over all of these local models. There are some hyperparameters then related to this federated training. In particular, you have to decide how many epochs or how many batch updates you do on the client in each global update round, but also, like, of course, the mini batch size and so forth. And it turns out that these values are, you might think that larger is better, but that's not always the case, because it becomes important to balance so that you don't have too large updates. For example, you can risk sort of overfitting locally on a client if you have, for example, unbalanced clients. So these are kind of important things that you typically then in a practical project need to look at a little bit and tune. And then I should also mention that there is a large and vibrant research community, of course, around these type of aggregators. And many improved versions has been updated as well. And typically, federated averaging is what we're going to use, and it works quite well. Yes. So a key challenge in a federated context is statistical heterogeneity. And this is something we also look at a lot. So if you can imagine then, if you have these kind of partitions and say that you have 10 clients, not all of them might have, the data might not be IID separated across these alliance members. And this, of course, affects convergence rates and accuracy. So what you can see in the figure here to the left is an experiment with a typical benchmark model called a data set called Cipher10. It's used a lot. Many of you probably have worked with it in machine learning, where we in this alliance, instead of splitting the data set evenly or IID, we created partitions where that only has a certain number of classes represented. So the clients are not seeing all data. And then what you see here is that, as this non-IDness becomes more and more extreme, it can really affect convergence and accuracy. And this is also quite a large area of research where you can try different things to mitigate these effects. In reality, then it's hard to tell in practical situation how non-ID it is. It's probably not as bad as the theoretical examples we construct in research to make a point here. So it's somewhere in between the ideal case and the worst case, I would say. But then there are approaches that you can do. For example, leveraging a small amount of shared data or use data augmentation to supplement clients with data points. But this is the problem of statistical heterogeneity, and this is a sort of important topic. Another thing about federated learning that is interesting is that of system heterogeneity. So that's another key challenge. So you can imagine that if you run this type of setup, all the clients might have quite varying hardware setups. Some of them might have high-end GPU workstations, where others trying to run on laptops. Depending on the use case, of course. I mean, we even do this on cell phones for IoT applications, whereas others might have regular, HPC clusters that they are joining from. So this is a challenge in orchestrating training and federated learning. There's a particular problem called stragglers that is interesting. That what if some clients finish their updates much slower than others? How do you handle that? And then there are different strategies and a lot of work going into there, playing back to this aggregation function as well. But there are different types of problems what you do. But you typically set a common deadline. But this too also affects, the convergence rates and accuracies that you will obtain in intricate ways. And the third challenge, which is the one that I am personally really interested in our lab, it's me and Salman Tour, is another PI there, is that of scalability. So obviously, if you have a lot of clients or if the models are large, that the updates you're sending is large, this simple picture that you see here is limited in that the orchestrator will become a central bottleneck in the system. So that is something that we have worked a lot to try to eliminate that in different ways. So we'll talk more about that. But the challenges here also are that the communication is happening usually over normal internet. So weak communication or weak connections and dropouts leads to sort of issues as well. So scalability is another challenge. And I think these three challenges is why it's also important to realize that federated machine learning problem is not the same as a typical distributed machine problem. They look very similar on the surface and they share similar primitives and construct from the computational point of view. But it is a fundamental difference that we have no control over the data partition for one thing. So if we are using a cluster with multiple GPUs to distribute training, we are in control of partitioning this typically pool data set so that we do it in a good way for parallelism in an IID way. We typically also have less system heterogeneity and less failure rates in an HPC system. So a federated learning system in that sense reminds you more of an asynchronous cloud parallel application. So things like resiliency, robustness to, like I said, statistical data, those things become very important. So for this reason, this is a quite different problem if you sort of look under the hood beyond the pictures. Coming to privacy preservation, that's of course a large field that you can look at from different angles. And typically we talk about input privacy, which is essentially about the privacy of in the machine learning context of the training data, like the data that goes into the algorithm. But then we can also talk about output privacy, which is essentially the problem of once you have the model, a trained model, what can you learn about the data that was used to generate it by access to it, by querying it or making predictions. So federated learning in its most basic form essentially is a very elegant solution to the input privacy problem. And it does that by essentially making sure that data never leaves the administrative control of the data owner. Yeah, so that's essentially one way to think about it. But with that said, I mean, there are many other sort of interesting technologies out there. So this one, I mean, to call privacy enhancing technologies. So homomorphic encryption is one of those that is heavily researched. My personal opinion is that it's not really mature for machine learning, but I mean, people are working on this. And what you do here is essentially, it's a way to compute directly on encrypted data. So you never need to decrypt the data. For example, to do an aggregation between two vectors, you can do that in encrypted space. So one encrypted and one encrypted becomes, the result is encrypted. So this is, of course, a way to compute without disclosing the data as well. But there are currently like challenges and limitations for like large scale systems. But this is one thing that people are looking at. Secure multi-party computation. And then the special case of secure aggregation is also something that is people are interested in. And this is about essentially, if you have a couple of parties and parties in an alliance, you want to jointly compute a function of local data. And the setting here is that you don't have trust between these parties. So what this is about then is protocols to emulate a trusted third party without having one. It becomes decentralized protocols. And there are ways to do this, and some federated learning projects also are focusing on this and picking it up. Differential privacy is something that is also very interesting for output privacy, and this is an idea where you sort of base this on a quite rigorous statistical framework, where the idea is that you add controlled noise to, for example, data or to weights, and then you sort of essentially average out this noise when you do the computation. So this can be a reasonable way then to also to mask input data and still be able to compute the result. And this is a quite old technique as well. It's used in context with federated databases, for example. So this is about sort of protecting output privacy. And why I bring this up as well is because of, if you read the literature, many of these techniques are used together with federated learning, at least in the research frameworks, in the sense that, for example, people they're adding differential privacy to the weights that are sent to the aggregator to protect them further, or use homomorphic encryption for doing the aggregation in a secure way, or secure multi-party computation for the same purpose. But then there is actually very little known, and it's a very hard problem in practice to say in what situations these techniques are actually needed and offer significant additional security compared to the input privacy that you get from federated learning. But the question essentially boils down to sort of, if you could obtain one of the weights vectors, or if you obtain the sum of the weight vectors, how do you invert the models that you can learn about the individual client data sets? So this falls in the area of adversarial machine learning, and it's not really different from that subject area in a non-federated setting. But this is interesting, and a lot of work is also going on in this direction. If we go back a little bit to the work we do with federated learning, in order to tackle challenges with scalability primarily, this slide here sort of illustrates the high-level model that we have built our system based on. So instead of a single server, we have the possibility to have multiple servers, and they are, in our terminology, called combiners. So these are the middle layer in the picture that you see here. And then we have something called the reducer, which is on the top level, and then you have clients on the bottom level. So when we do federated training, we typically have the controller that sits on the top level. It delegates responsibility for aggregating models from a number of clients to one combiner, one or many combiners. So if you have many clients, you can have multiple combiners, and each combiner has a sort of independent responsibility for a subset of the clients. And then at the end of such a round or a global round in training, federated training, we employ some reducing protocol then over the combiners to produce the global model. And we do it this way because then we can easily scale the combiners in what we call the combiner network horizontally by adding more and more machines there to accommodate more and more clients. This is essentially, if you are into computing, it follows the MapReduce programming pattern, but it's not essentially implementation. It's nothing like MapReduce, but it has the same sort of structure. And that's also a pattern that we know, I mean, from computer science, that this will have very good properties when it comes to massive scalability. But you can look at the special case, of course, where you only have one combiner. I think this is the setting we will actually do in the lab today because we're not that many clients. You're sort of back at the central server, single server setup that is employed in most other frameworks. Are there any questions so far?
Can I ask a question?
Yes.
So it might be a naive question, but maybe it will be easier for me to explain or ask my question if you show the slide that you showed the 3 different models to predict the accuracy of prediction of the human blood cancer cell. That was slide number 3. Yeah,
number
3 or 4. Yeah.
Yes. This one. No, this one.
This one, yes, exactly.
Yeah.
So here you showed that the best local model has a lower prediction compared to centralized global model and federated.
Exactly. Yeah.
And so that's interesting. And I was just thinking about other angles of this scenario. Is it more like cost effective or time efficient using these new methods compared to like best local model?
See if I understand the question. I think just to reiterate, the fact that the best local model is worse here is because it sees less data, right? So that part is clear. But then I wasn't exactly sure what you were asking there.
So my question is that so the beauty of this method is only using more data, right? And distributed on different institute or different
exactly.
Okay.
It unlocks data silos, and then whether that additional complication is worth it. But I mean, also, like, it's important to remember, like, because to even produce these type of plots that you see here, we have to have a centralized model to compare to, right? So we do that when we start with an open data set like this that can be pulled. But in the situations that you would target in the real world, that is not an option. So this orange curve that you see is unattainable. That doesn't exist in the real setting. But of course, it is interesting to produce it in order to do research on the efficiency and convergence of federated learning. But the alternative to federated learning in this setting would be to have a data sharing agreement so that you can copy all the data into the same cluster. And then you can compute the orange curve.
I see. Yeah.
And that would likely then require, more anonymization strategies and that kind of stuff. So that's the setting.
Yeah, thank you.
So you trade that complexity for a complexity in having to work with a highly distributed system.
Thanks.
Yeah, no problem.
Can I ask another question?
Yes.
I mean, along the same line, you mentioned about having access to different data sets in different, let's say, clients. My question is, it's a matter of now distribution problem. No, you have data, difference. I mean, there are differences in their quality, in distribution, and how you can control your accuracy. Like, how do you know that you're really converging other than, just, especially since we are talking about SGD, how do you know that you're not just walking around some minimum?
You mean globally?
Yeah.
Yeah, I will come to that. But of course, you have to have some way to validate. So either the clients will have to have local validation sets, and then this is what we will look in the lab, one such setting. And then you can also, I mean, of course, you can then track the progress in the training by looking at the loss or accuracy. Or you can agree, it could also be good to have some small amount of, or at least some shared validation set that has been cleared for being shared. But you follow the same strategy as you would do in normal machine learning. Although you now get for example, if all the clients have their own train test split, you now have sort of a distribution of losses and accuracies over the alliance, and then you have to decide essentially what constitutes an improvement. Is it the average or max or min or median? But I think we can look a little bit at that also when we do the lab. Does that answer your question?
Yes. Yeah,
that's
good.
You. Yeah, so I will not go on for too long, but I also thought that another way to look at FedN, which is the system we have built and are working with, is this picture here. So that's another way to look at this, more sort of how we think about it when we actually go and deploy the software. So we have a loosely uncoupled network of combiners that each, so when a client connects to our system, it gets assigned to one of these combiners, and then this is essentially the reducer which runs a discovery service, and then there's a controller also that programs against the combiner network and coordinates these kind of training cycles. And yeah, so this is how it could look like as well. And a good thing with this is that, and why it's designed this way, is also because then you can also deploy these combiners, taking into consideration both regulatory issues, but also performance issues. We can deploy a combiner, for example, close to a client group. So say that you know that you have a bunch of clients at SciLifeLab in Uppsala in the facilities that should connect. You can have a combiner running in SciLifeLab. But if you want to collaborate with similar groups in the US, you can have a combiner running there as well. So this is a way to sort of reduce the traffic over the internet if you have large number of models. This is particularly interested for the edge IoT mobile computing case. Yeah, so this is the software we have developed. Another thing I just wanted to say about it a little bit architecture-wise in a high-level overview is that communication is based on something called gRPC, which is a Google RPC service. And then we use like a and now this becomes for you techies in the audience there, that we use protocol buffers to essentially standardize the messages. Because it's important, we think that particularly the client side of the solution can be implemented in multiple different languages. So this we have ensured in this way. But we also have a very modular and pluggable architecture. For example, it should be possible to, as a user, then modify or replace these aggregation algorithms, and also modify this global control strategy. So all of this is possible in the solution if you are a developer. Then you need to know a little bit of software engineering, but it's nothing super fancy in that sense. So that's what this slide was about as well, that you can really adapt the framework in the way you see fit. And I can mention that we have an archive publication up that you can read if you're more interested in the work that we have done. I mean, Ola gave a nice overview also to what is done in the wider context, but this is work that we have done here at the IT department in the collaborations with Ola's group in the company. So what we have done here is looked at two use case essentially directions. One we call the cross silo case, which I think is the case that would be most interesting for you guys in the life science community, where we assume that we have quite like large, in this case, neural networks. We did this with a natural language processing model. And the clients are they are typically representing maybe a research group or a larger center, and they have some reasonable hardware. But like I said, models are quite large. So here we did experiments with this combiner network deployed in 4 regions of the Amazon cloud, geographically spread out, and up to 40 clients, each updating NLP model that was like 1 gigabyte in size. So in every round, essentially, we're communicating 40 gigabytes worth of data. And when we did this benchmark, it was a few months ago, we arrived at sort of a network data throughput rate of about 450 megabytes per second on a 1 gigabyte theoretical line. So that's quite good. It shows that we can sort of accommodate scaling for large models. But you can also look at the case of very small models and very, very many clients, and then a resource constraint setting. So this we also did. And this is interesting for IoT applications, Internet of Things, where we show that also you can handle thousands of clients on a single sort of resource constraint combiners if the model updates are small. And we have done a lot of work, of course, on the implementation and architecture, but we also get a lot of performance from gRPC, which turns out to be a very good choice for a framework for implementing this type of systems. We talked a little bit already in the question about the validation, but this is interesting in the federated context because we can essentially choose to validate during training on different levels. And these pictures illustrate that. So we can have validation happening on the client side during training, but we can also imagine setting up validator nodes on the combiner level or even on the global level. And I think if you were to form a real federation to solve a problem together, this is something that you have to talk about as well and agree upon how validation should happen. Because obviously, one promise with federated learning is that by accessing more data, you train a model that generalizes better. But there is no guarantee that in each round that you're going to improve every single participant's local model if it's only measured on that client's local data. And this is an important thing to think about when you think about federated learning. But what can also be done there, and what there is also research done on, is of course personalization of the model or local adaptation. So like you train a highly generalizable model, but then you can also, of course, if that's okay for everyone, do local adaptation to your to fine tune to your local data sets essentially. So this is also one way to use it if you have a lot of, especially if you do this in a non-competitive or non-commercial setting. So that's many things are possible, but that falls a little bit out of the scope of federated learning because that's essentially taking the final result of the federated training and then working further with it. So I wanted to end this part with a few also hints by why this is interesting from an e-science perspective. And I mean, everyone has their own favorite, but I think it's a really interesting research problem from the performance and scalability point of view. Essentially, how do we design frameworks and algorithms to work well and to be highly performant? It's tied to also to usability, because they also need to be reasonably easy to use. Security is, of course, at the heart of this challenge. Like, how do we make the systems robust to dishonest members in the alliance or external threats? So this is something we're pushing in the company as well. We're doing Vinnova projects, for example, in looking into something called trusted execution environments to increase trust. We have also done work with blockchain as a way to guarantee that you cannot actually tamper with a model training trail. So we're not communicating with a blockchain or putting models on a blockchain, but we can use it to make sure that the audit trail of what is happening in the alliance during training cannot be tampered with. which can be important for trust. And of course, the centralized computation. So how can we eventually do all of this without a central coordinator? So that's also an area that we work on. But I think I would like to stop there. And I think we should take a break for 15 minutes, right, Ola? That's the plan. And then we will continue with a hands-on part. But I think we have time for some questions if you have questions.
So I can start with asking you a question then, Andreas. So
Yes.
Can you say something about how FedML, the system, is developed in a sense? I mean, it is an open source project, right?
Yes, I should have mentioned that. Yes, it's an Apache 2 project, open source project. So it's a collaboration between primarily my group and the company that we have founded as well. But all of the code is open source on Apache 2. That's important to us. You will also see in the hands-on part a full-fledged like end-to-end machine learning or MLOps for the centralized AI platform. That's what we're going to work with later, called Studio, which is developed by Scaleout, but that is also in principle an open source system. And I don't know if you want to say anything more about that, but yeah, it's all open source.
Yeah, and would you be open to academic collaborations if people are interested in sort of doing things in federated machine learning?
Yes,
a problem and so on.
Yes, of course. So both applications and improvements of the algorithm are highly interesting, and both. I mean, you can have both collaborations with the company, but also with my research group, obviously.
So more questions, both to Andreas and to myself. We will stick around. So yeah.
Actually, I had another question. You mentioned about encryption, that you can encrypt data before sending it to the algorithm, and then that vector would be sort of nonsense if we look at it. But then there's going to be a parameter map that maps the parameter of the model that we train on encrypted data to real data. And my question is, can we assume that if we do this map, then the model will work? Like this is given or not? We just take it as a like the rule of thumb.
I think it will work. So first of all, to be clear, I mean, we don't actually do that in FedML.
Okay.
I don't think we will do homomorphic encryption either anytime in the future.
Okay.
Because I don't think it will work. I think the overhead of doing it is too high. I think the secure computation is a little bit more scalable if secure aggregation, if you want to do that. Well, of course, we encrypt the data in transit and in rest. But I mean, that's we do that with TLS SSL, and then I'm decrypting computation. And I think it's also important to remember that you have a lot of privacy protection just by shuffling the client updates. You don't really know where they are coming from.
Okay.
But I think when you bring that up, I think that the homomorphic encryption research part, there is some very interesting work, but it's only working for very limited models today. And that's not encrypting the data, it's encrypting the model itself. So you have clear text data, but you train the model in encrypted space. And that's a little bit elegant, because then you have a model that no one can use unless you have the key.
I see.
But that's a kind of different thing. There's a group in Canada that does that. So that's cool. But no, we don't do that in FedML today. It's something you could easily add, but we are currently happy with TLS SSL encryption there.
I see. Thank you.
Yes.
Okay, if there are no more questions, then I would propose we take a break and welcome back. There's another for the hands-on workshop. We will be assisted by some other people here, also from Scaleout, to do the exercise. We will build up a federation and also try to start local clients and so on, and joining a federation. There's a separate workshop, separate Zoom link sent out for that. Since we had a few late cancellations, then contact me privately on the practical part. You can just write in the chat here, and I will send you the Zoom link for that. And then Gunnar has a question for you, Andreas.
Morgan, are you here yet?
Yes.
Yes. Do you want to answer? Do you have end-to-end encryption in the data exchange or only HTTPS? And with data exchange, I assume, Gunnar, that you mean the weights that are sent, because the data is never sent, is never exchanged. Yeah. So the model update is communicated.
Yeah.
Not currently, no. But it's something that we can and are planning to implement as we go further.
Yeah, I have some advice there, how to implement it nicely.
Okay, we can talk about that. Yeah.
Great.
Okay, we see you in 15 minutes then.
Yep. Will do. And then I will also start with a small introduction to the workshop, and I will show you a little bit of what Scaleout Studio looks like in that session.
Thank you, everybody, for joining.
Thank you.
Good.